So in this lecture, we're going to talk about predicting branches and how to handle exceptions. So the contents of the lecture, we're going to start out reviewing the branch delay slot. We're going to talk about the performance cost that we had from the branch delay slot, and we're going to talk a little bit about how we can reorder instructions to fill the branch delay slot. We're then going to look at a really simple way of predicting what a branch does, and that is we're going to predict it's not taken. And when we're wrong, we have to clean up from having the wrong instructions executing, so we're going to talk about how to kill instructions when we're wrong. Then we're going to go on and look at some other static branch predictors. That is, branch predictors that don't change based on the behavior of the branch. We're going to see there are a bunch of different ways to do this, but they don't work all that well. So that's going to motivate us to look at dynamic branch predictors. So we're going to look at some examples of loops and how they work, and we're going to talk a little bit about how the processor is going to store which branches are taken and when. Finally, we're going to spend some time talking about exceptions and interrupts and what they are and some of the issues that we have with them in pipelines. So what material is not in this lecture from the book? Well, actually most of the stuff is in here, and there's a bunch of extra stuff in this lecture that isn't in the book. So now let's talk about the branch delay slot. Remember what we saw before. So we have this problem with a branch that it takes a long time to figure out whether it's taken, and we saw that in our standard MIPS pipeline it takes a whole bunch of cycles. So 3 cycles until we know, because we don't find out until we get to the 4th stage in the pipeline. So what we said was, well, we can just stall. We can just put in bubbles in the pipeline for those 3 cycles. And this works fine. So this is correct whether or not the branch is taken, because we're just putting in no ops, but it wastes 3 cycles. So this is an incredible waste of processing power in our processor, and so we want to try and avoid doing this. We talked about ways to avoid this, and the first one was let's move the branch computation earlier. So when we had the branch over here in the mem stage, it took us 3 cycles. If we moved it forwards one to the EX stage, we could do it in 2 cycles, and of course if we move it even further into the instruction decode, we could do it 1 cycle. And we talked about how to do this. We need to put in some extra hardware. So we need an extra adder to calculate the new address. We need an extra comparator to check and see if the registers are equal to see if we should do the branch. But when we put that in, we can now do everything in just 1 cycle. So by moving everything earlier, we now have this state of affairs, where we can detect our branch earlier and decide it, and so we only have 1 cycle that we need to wait for the branch to be resolved. So this 1 cycle right here we said is called the branch delay slot, and if we can put something in there, then that's great. So if we can find an instruction to put in there, then we can get the full performance. So a lot of work is how do we keep the branch delay slot full? So what is the performance of having this branch delay slot? How much does this really hurt us? Well, so for every branch, we're going to use 1 extra cycle. That's the branch delay slot. Branches are 17% of all our instructions, so we're going to have an extra cycle for every branch. We're going to be 17% slower. Now that's not so good, but if we can change our code around, that is reorder our code to fill the branch delay slot, then we won't have this performance penalty. So let's take a look at an example of doing that. So here's some code that we have, and you can see we have an add instruction and a branch instruction. Now the add instruction here is always executed, and it's independent of the branch. So it doesn't have to happen before the branch. So what we can do is we can move that add instruction to somewhat later and put it in the branch delay slot. So here's the code where we've done that. We've taken the branch instruction, we've moved it up 1, and that allows us to take the add instruction and put it in the branch delay slot. So because we put something useful in our branch delay slot, we've now reduced the length of our code. We saved 1 instruction by filling that no op in the branch delay slot with something useful. So the summary of branch delay slots is that they're okay for 5 stages. So we saw that by moving a logic forward, we could reduce the branch penalty to 1 cycle, and we can often fill a single branch delay slot. So this isn't too bad. The problem is that modern processors have 15 to 20 pipeline stages. So many, many more stages than our simple 5-stage pipeline. And in this case, we can't fix them by just moving the branch calculations earlier. And we can't fill more than 1 branch delay slot reliably. It's hard enough to find an instruction for every branch to use. If we have a much longer pipeline, we may need to find 10 or 12 instructions for every branch and that just isn't possible. And obviously we can't stall, because if stalling in our 5-stage pipeline hurt us a lot, stalling in a much longer pipeline is going to hurt a lot more. So let's go back and see what the fundamental problem was here. And that problem was that it takes time to figure out whether a branch is taken, and we have to wait for the branch to resolve before we know what to do. So if we have to wait for it to be resolved, the only way around this problem is pretty much, well, predict the future. If we could predict what the branch is going to do before it does it, then we can go ahead and do the right thing ahead of time. And that's what the rest of this lecture is going to be about. So a question: why would it be hard to fill the branch delay slot on a modern processor? Well, the answer to this is that it's hard to find a whole bunch of instructions that are executed regardless of the branch. So on modern processors, we have much longer pipelines, and that means we need many more branch delay slots. So we've seen that it's hard to find a single instruction to fill a branch delay slot. If you need to find 15 for every branch, it's going to be impossible. So programs just don't have enough instructions that are independent of branches to be able to fill that many and that long a branch delay slot. Here's a question. So look at the code down below here, and which of the instructions that are highlighted can we move into the branch delay slot? The answer here is that we can move the AND instruction. So the AND instruction here is executed whether or not the loop is taken, the branch is taken, and it's independent of the branch. So we can go ahead and move it up there and put it in the branch delay slot and make our code shorter and make it run faster.